Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I am taking wave mechanics for chemistry. This is lecture number 15. In this lecture, I will explain you Hamiltonian operator. That is H, or it is total energy operator. For different atoms or ions. So first of all, I'll take for H2 plus 1. Okay. So our aim is to find out total energy of H2 plus 1. Now hydrogen, H2 molecule. The configuration is 1s2. It has 2 electrons and both electrons are in first orbit. But when you take H2 plus 1, there are 2 hydrogen atoms and 1 electron, and that is in 1s1. Okay, so the figure would be like this, that there are 2 different hydrogen atoms having 2 different nuclei. Suppose this is the nucleus of first atom, we call it A, and nucleus of second atom, we call it B. Then this distance, which is normally bond length, we call it RAB. And now there is only one electron. Okay, so we call it E1 or E only, and this is negatively charged. The distance between an A nucleus and E, we call it RA, and the distance between B nucleus and electron, we call it RB. Okay, so here the electron and nucleus A attract each other, so there will be attraction over here. Similarly, electron and B nucleus also attract each other. So again, over here you will find attraction between nucleus and electron. But 2 nuclei having same charge, they repel each other. So there will be repulsion between these 2 nuclei over here. Okay. So now if we consider potential energy when there is attraction between 2 particles, then it will be always negative, and it is minus z square upon distance, that is Ra. Similarly, over here there is attraction between nucleus A and electron, so potential energy between these two would be minus z square upon Ra. Sorry, I made a mistake over here. This is nucleus B, and therefore here it should be RB. So on this side the distance is RB and over here the distance is RA. So potential energy for A nucleus and electron is minus Z square upon RA, and potential energy between B nucleus and electron would be minus Z square upon RB. But there is repulsion between 2 nuclei over here, and therefore potential energy will be positive over here. So plus Z square upon the distance is RAB. Okay, so this is potential energy of this one. And now we consider total potential energy. And for that we use capital V in Schrodinger's equation, and that is minus E square, addition of all potential energy. So as Z is equal to 1 for hydrogen, so we are taking Z equal to 1, okay, for all. So Z equal to 1, that is atomic number of hydrogen. So minus E square upon Ra minus E square upon Rb plus E square upon RAB. Okay, so Hamiltonian operator for H2 plus. Let us see this one. Hamiltonian operator H is equal to minus h square upon 8 pi square m Laplacian operator del square plus potential energy. Okay, as there is only one nuclei, there are two nuclei, but there is only one electron, therefore Laplacian operator remains the same, del square. So H would be minus h square upon 8 pi square m Laplacian operator square plus, instead of V, now we'll put this one. So now there will be no positive sign, but we start with negative sign over here, minus E square upon RA minus E square upon RB plus E square upon RAB. So this will be Hamiltonian operator for H2 plus. So now we will see Hamiltonian operator for H2 molecule. Now H2 molecule has two hydrogen atoms. Okay, so H2 is equal to 1s2, which we have seen, and there are two hydrogen atoms. So there will be two nuclei. One is A, another is B, and there are two electrons of each one. So this is E1 and this is E2. Okay, so this is for one hydrogen atom and this is for second hydrogen atom. Okay, now the distance between nucleus of A hydrogen atom and first electron, we call it RA1. Okay, similarly, distance between nucleus of B hydrogen atom and E2 would be RB2, and there is always attraction over here. On this side also there is attraction. Okay, now this nucleus A would like to attract E2 electron, and the distance between these two would be RA2. Similarly, E1 will be attracted by nucleus B, and this distance we call it RB1. Okay, so this again there is attraction over here. Now E1 and E2 definitely repel each other. So there will be distance between these two is R12, and similarly distance between two nuclei A and B we call it RAB. So majority we see that R12 there will be repulsion, and here RAB also there will be repulsion. Rest is attraction. Okay, therefore total energy, total potential energy V would be minus E square upon RA1 minus E square upon RB2. Here we will consider Z is equal to 1 because hydrogen and atomic number of hydrogen is 1, minus E square upon RA2 minus E square upon RB1. Okay, and plus E square upon RAB plus E square upon R12. Okay, so this is total potential energy for hydrogen, and therefore for hydrogen Hamiltonian operator H would be minus h square upon 8 pi square m. As there are two electrons, so we will take two Laplacian operators, del 1 square plus del 2 square plus potential energy V, and for that we will put this whole sequence. So H would be minus h square upon 8 pi square m Laplacian operator 1 square plus Laplacian operator 2 square minus E square upon RA1 minus E square upon RB2 minus E square upon RA2 minus E square upon RB1. Sorry, it should be RB1. And plus E square upon RAB plus E square upon R12. Okay, so this is Hamiltonian operator for H2 molecule. Okay, similarly we can take He2 atom, sorry, helium atom, and in helium atom there will be only one nucleus and two electrons. So H for, that is Hamiltonian operator for helium atom. Okay, now let us see this one. Helium atom, there is only one nucleus. Okay, we call it A. There are two electrons, E1 and E2. Okay, and there will be attraction between nucleus and two electrons. So this is the distance between Ra and one electron. This is the distance between to second electron and A. So we call it Ra2. There will be attraction between Ra1 or A and E2, as well as attraction between E1 and A nucleus. And E1 and E2 repel each other, so this distance is called R12. Okay, so there is the repulsion over here. So the net potential energy for helium atom would be minus Z square upon RA1 minus Z square upon RA2 plus Z square upon R12. Okay, in this case Z is equal to 2 and E is also common, so we write V is equal to minus 2 E square common into 1 upon RA1 plus 1 upon RA2 bracket complete plus E square upon R12. Okay, so here, sorry, E square is common, so it should be Z square upon R12, and this way we can write this one. So now Hamiltonian operator H for helium would be minus H square upon 8 pi square m. As there are two electrons, so we take two Laplacian operators. Okay, and then V, so for that we write minus 2 E square bracket 1 upon RA1 plus 1 upon RA2 plus 2 E square upon R12. Okay, so this is H for, or Hamiltonian operator for helium atom. And similarly, we can have Hamiltonian operator for various elements depending on their structure. Okay, that's it in this lecture. Thank you so much.